Okay students, welcome to the next lecture of switching theory and logic design. In this video, we will discuss about implementation of Boolean functions using multiplexers. Right. Let us take a small review about 4:1 multiplexer. 4:1 multiplexer. Right. So this is the generalized block view representation for 4:1 multiplexer. This is the generalized block representation for 4:1 multiplexer. So where 4 is representing inputs and 1 is representing the outputs. So here the inputs and output combinations we are representing with this notation. Coming to generalized notation, we will represent 2 power n=1 multiplexer. 2 power n=1 multiplexer, where n is the selection lines, n is the number of selection lines, and 2 power n is number of input lines, and 1 is the output line. So this is the generalized representation for multiplexer. Here I am discussing about a 4:1 multiplexer, where 4 are the inputs and 1 is the output, and S1, S0 are the selection lines. The information signals I0 to I3 are the 4 input signals. These input signals, any one of the input signal will be present at the output channel based on the selection lines information. So here we can define the multiplexer. We can define the multiplexer in this way. So where the multiplexer is a device which the output of the multiplexer is the any one of the input based on the selection lines. So remember, once again I am defining the multiplexer definition. A multiplexer is a device which consists of many inputs and single output and some selection lines. Now coming to the definition of multiplexer, the output of the multiplexer is any one of the from the 2 power n input lines based on the n selection lines. This is the definition of a multiplexer. So in this multiplexer we have 4 inputs, that is I0, I1, I2, I3. But the selection is completely depends upon the S1 and S0. So here the S0, S1 lines I have mentioned here. The maximum possible combination for S0 and S1 signals are 0, 0, 0, 1, 1, 0, 1, 1. And coming to the output y is equal to here whenever the combination 0, 0 selects the I0 is equal to the output. That is I0 went to the output. So the output y is equal to I0. Whenever the combination you select 0, 1, the output y is equal to I1. Whenever you select the combination 1, 0, the output y is equal to I2. And whenever you select the combination 1, 1, the output is I3. So these are the 3 or 4 input possible combinations for the 4:1 multiplexer, and those 4 are the output signals. This is the truth table of the 4:1 multiplexer. Next, coming to the internal circuit diagram of the 4:1 multiplexer. Before going to the this detailed internal diagram, first write down the output expression for the 4:1 multiplexer. The output y is equal to, here we have 4 functions. So actually previously here we have either 0 or 1. If 1 is there, then we are writing the input minterms combination. If 0 is there, we are leaving that minterms. But here we have the output I0, I1, I2, I3. Here 0 is there, we don't know. If it is 1, we don't know. We don't know the value of I0, I1, I2, 3. So for that reason I am writing like this. If the y is equal to the first one, I0, that is the output. If it may be 0, we will get here. That is nothing happened to here. So I0 into, that is S0 bar into S1 bar. So this is the first output. So if it is 1, so the 1 is completely based on the main term. So see here, where this is the I0 and this is the small m1. If it is 0, here there is no term. If it is 1, only m1 will be available. So there is no doubt at all about this function. This function is I0 into S0 plus S1 bar. Next, coming to here, not only I0, we have 3 more cases, that is I1, I2, I3. So I1 into S0 bar into S1 plus I2 into S0 into S1 bar plus I3 into S0 into S1. So this is the output functionality. Okay, so I am writing again here, y is equal to I0 into S0 bar into S1 bar plus I1 into S0 bar into S1 plus I2 into S0 into S1 bar plus I3 into S0 into S1. So this is the finalized output function. Right? So this is the output functionality for the a multiplexer. So see here we have totally 3 midterms. So this is the one product term, this is the one product term, this is the one product term, this is the one product term. Totally we have used 4 AND gates operation, and these 4 AND gate outputs we are summing. So see here, this is the plus symbol, this is the plus symbol, and this is the plus symbol. So here we have 4 AND gates and 1 OR gate which consisting of 4 inputs. So this diagram we are implementing in this way. So you can write down. So here AND gates, the first AND gate, second AND gate, third AND gate, and fourth AND gate. Okay, 1, 2, 3, 4. So these 4 outputs are we are connecting to an OR gate. So this is the diagram. Here we have 4 AND gates. This is I0 into S0 bar into S1 bar. Here I1 into S0 bar into S1. Here I2 into S0 into S1 bar. Here I3 into S0 into S1. So here we have 3 inputs. 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 Okay. So here the first one, this is I0, and this is I1, and this is I2, and this is I3. And S0, S1, S0, S1, S0 bar, S1 bar. Here you have to use a NOT gate, and this is S0, and this is S1. Okay, S0 and S1 signals are available. So here S0 bar, S1 bar. So take a dot here and represent this one. S0 bar, S1 bar. Here S0 and S1. Okay, this is S0, S1, S0 bar, S1 bar. Next, S0 bar, S1. Here S0, S1 bars. So this is the simplified diagram or internal structure of 4:1 multiplexer. Okay. So here I am represented with this logic diagram representation. So whatever the output here we have, that output we have mentioned with this operation. So see here, S0, S1 signals are there, I0, I1, I2, I3 are there, 4 AND gates and 1 OR gate. So this is the internal structure of 4:1 mux. So that 4:1 mux internal diagram or logic diagram or hardware implementation is related to this picture. Okay, right. Now here our task is 4:1 multiplexer we know, 8:1 multiplexer also we know, and how to implement higher order multiplexer here by using lower order multiplexers also we know. Here our target is, here we have a problem. That problem statement is implement f of ABCD is equal to sigma 0, 1, 4, 6, 7 using 4:1 mux. So this Boolean function we have to implement by using a multiplexer. So that multiplexer also is a 4:1 multiplexer. So here this is the function. So previously we have seen y is equal to, we have written some function that consisting of 2 input terms S1, S0. Okay, so see here the given Boolean function f function is equal to sigma small m of 0, 1, 4, 6, 7. 5 minterms are available. Actually, with the 3 inputs, we will get 8 maximum possible combination, that is 8 minterms are available. In the 8 minterms, they given 5 minterms. For these 5 minterms, we have to draw the logic diagram with the help of 4:1 mux. You have to use 4:1 mux. For that, first you have to draw the table. So these are the ABC signal and these are the maximum possible combinations. And this is the F output signal where the 0, 1, 4, 6 combination. So see here, so this is the G first here, F is equal to 1 is available. So that is the first combination M1, and this is the next M2, and this is nothing but as M4, and M0, M1, M4, M6, M7. So this is M0. This is min term 0, this is the min term 1, and this is the min term 4, and this is the min term 6, and this is the min term 7. These are the 5 min terms are given in the given function, in the given problem. Now here our target we have to implement by using this one with 4:1 multiplexer. We have to implement with the help of 4:1 multiplexer. For the 4:1 multiplexers, we have only four information signals and 2 selection lines, 1 output. Right? So now how to solve this problem? Here we have inputs are ABC. Here we have ABC inputs, 3 inputs are available. Here we have only 2 selection lines. S1, S0 only available. Why? Because the information signal, if it is 0, output is 0. If it is 1, output is 1. Okay, the maximum possible combinations are available at the selection lines 0, 0, 0, 1, 1, 0, 1, 1. So now our target implement this function by using 4:1 multiplexer. 4:1 multiplexer we have to implement the operation. Right. Now see here how to implement this function. Now let us take a small table which consisting of ABC inputs. Why? Because here we have only 2 selection lines. The 2 selection lines I am taking as A, B input terminals. So for the multiplexers, I have 2 input lines S1, S0. Those S1, S0 I am treating as AB. I am treating as AB. Here I have two input combinations with the possible combinations. That is A bar, B bar, A bar, B, AB bar, and AB. These are the 4 input combinations for the AB. And coming to that, remaining one is C. So C has a C bar and a C. These 2 values. Okay, right. Now, so see here, A bar, B bar, and this is C bar. So A bar, B bar, C bar. The minterm value I have written here. This is 0. That 0 indicates M0. That 0 indicates M0. And A bar, B bar, C. This is indicates A bar, B bar, C. That is 0, 0, 1. That is here we have minterm 1. 0, 1. Next 0, 1. A bar, B bar, 0, 1. And C bar 0. 0, 1, 0. That is equal to minterm 2. 0, 1, 1. That is A bar, BC. A bar, BC nothing but as 0, 1, 1. That is equal to 3, M3. So 0, 1, 2, 3, 4, 5, 6, 7. I have written the minterms in this way. I have written the minterms in this way. Now, see carefully the given problem. The given problem has f of ABC is equal to sigma small m of 0, 1, 4, 6, 7. So these values you have to round up here. These values you have to round up here, the first thing. So here 0 is there. Now right over here you have to represent the 0. Right? So here I have represented the 0 in this way. So 0, 1. So see here I have highlighted the 0, 1 terms. Next 4th term. So I have represented 4. Next term 6. So now 6 I have highlighted. Next coming to the 7. So 7 I have highlighted. So totally I have highlighted the totally 5 terms 0, 1, 4, 6, 7. So the 0, 1, 4, 6, 7 I have represented. Now coming to here A bar, B bar. So the A bar, B bar covers C bar. 2 terms it is covered. Okay, if 2 terms are covered, then you have to represent the final value as 1. If it is not covered, then you have to represent 0. If it is covered only C bar, you have to write down C bar. Now it is covered 2 terms that you have to represent 1. It is very simple thing. Check that A bar, B bar. A bar, B bar, the 0, 0 values are covered with C bar and C. So that yellow color parts we have represented. In the given problem, 0 and 1, two values are available. So for that reason I have represented with 1. Okay. So if two values are covered with this given product terms, with the given problem, then you have to represent answer is 1. If it is not covered at least 1, then you have to represent 0. If it is covered only 1, check that the single value is what? That is C bar. You have to write down here C bar. Now this is covered 2 times, then you have to write 1. If it is covered only 5, then you have to write down C. Like that you have to mention. It is very, very important. Okay, right. Now I have written the values here. So this is covered, these two values are covered. So for that reason I have represented 1. Here no values are covered by the given problem. So I have represented 0. Here only 4 is given for the AB bar combination. So I have written only 4. And the AB value is covered by 6 and 7. So for that, in the given problem is 6 and 7 is are available. So for that reason I have written 1. So if two values are covered, you have to write 1. If one value is covered, you have to write down that C bar or C value here, and remaining values are not covered. If you have in the one combination of AB values, then you have to represent the 0 combination. Okay, right. Now next work. Now you have to remove this I0, I1, I2, I3 values. Okay, so just remove that values. Okay, now coming to that S0, S1, S0 values also you have to remove. Right? We have removed. So I0, I1 values. Previously here we have I0, I1, I2, I3 values. We have removed those values, and now S1, S0 values also we have to remove. So we have removed those values. Okay, right. Now in the place of this, you have to write the AB values here. In the place of selections lines, you have to write AB. Here you have to write AB. Now, so see here, if it is 0, 0, this line selects. If it is 0, 1, this line selects. That is, the first line indicates A bar, B bar. That is, we have represented here, first one. Next, second line is, here it is 0, 0. Next, 0, 1. That is A bar, B. That is, we have represented here A bar, B. Next, this is A, B bar. This is A, B bar. That is, we have represented here. And the last one is A, B. That is 1, 1. So, we have represented here. Right? Is it clear? Right. Now, we have the same order. Here, whatever the order is there, here also we have the same order. Right. Now what we have to do here? So whatever the result values came here, those values you have to write here. So here you have to write 1, here you have to write 1, here you have to write 0, here you have to write C bar. You have to write C bar. Okay, with this the problem is completed. Right? I have written these values. I said this problem is completed. How? How the problem is completed? So see here. Now I have mentioned here the values. Now we have to check our functionality. Right. So here, now you have to go back to your home problem. So that home problem is this one. F of ABC is equal to sigma small f of 01467. That is, for the minterm f0 is there, the output is equal to 1. Now you have to check the y is equal to 1 or not. Right? Y is equal to 1 or not. So remember this one. So I have removed everything. Okay, right. Now come back to our original problem. Now we have given A, B values, and here the 1, 0, C bar 1 values we got from the previous table. So from the previous table we have those two values. So this is the problem. This is the problem. So this is the problem. F of A, B is equal to sigma 0, 1, 4, 6, 7. Those values we have mentioned here. So this is the 0, 1, 4, 6, 7. For these combinations of inputs, we got the output values. For the combination of these inputs, we have the output values 1. Okay. For the remaining, we have 0. Now I said that F is nothing but as Y. Here Y is equal to nothing but as F. Okay. Right. Y is equal to F. Right. Now select the first combination ABC. 0, 0, 0. Right. So AB values are 0, C value 0, A value 0, B value 0. Here we are not giving any C value. Here there is no C connections. We have left that value. Okay now. So when you select AB is equal to 0, 0, what is the which input we are going to select here? So this is 0, 1, 2, 3. Okay. When you select 0, 0, the 0 line will select. At the 0 line we have one value. That one value is going to the output. Now Y is equal to 1. So the Y is nothing but as F. We have mentioned here F. So this is the F is equal to 1 combination. Right. Now check the combinations of the inputs, and here we have the first combination. Triple 0, next combination of 0, 0, 1, and next combination of 1, 0, 0, next combination is 1, 1, 0, and the next combination is triple 1. For this 5 combination, the output is going to 1, 1, 1, 1, 1. For the remaining combination, the output is 0. Let's take the first combination 0, 0, 0, where A is equal to 0, B is equal to 0, C is equal to 0. Here we have A is equal to 0, B is equal to 0. Here we have selection lines of A is equal to 0, B is equal to 0. Now write down here 0, 0. Now write down here 0, 0. So this is 0 and this is 0. Okay. If you select the AB is equal to 0, based on the multiplexer definition, the 0 line selects here, and this is the 0 line. 0 line, 1 line, 2 line, 3 line. Okay. When you give it 0, 0, the first input goes to as output. Here at the place of first, at the 0th line, we have the value is equal to 1. Now F is equal to 1. So here the output function F is equal to 1. So we got the answer 1. Right? Next we will check the next combination. Okay. For the next combination, 0, 0, 1. Here I have kept 0, 0. Now I have kept the values of A is equal to 0, B is equal to 0. Here, whenever I select the AB is equal to 0, the first 0th line, here 0 indicated line, the first input of the multiplexer goes to the output. The first input of the multiplexer is equal to 1. Now output is equal to 1. So the same condition here repeated. Here we don't have the C value. A is equal to 0, B is equal to 0. For this two combination, here I have kept A is equal to 0, B is equal to 0. So here there is no, I am not giving any C value. So based on these inputs, the output will come. Okay, that is over. Next, coming to that, next combination, 1, 0. Here see here, 1, 0, 1, 0. Now here you have to keep the values as 1, 0. That this is the 1, 0. If you select here 1, 0, then automatically the third was the second terminal output, that is, see here 0, 1, 2, 3 is there, the two represented terminal will select here. So here I have taken the combination of ABC is equal to 1, 0, 0, 1, 0, 0 I have selected here. So the 1, 0 we have taken as AB values and C value is equal to 0. Here AB is equal to, if it is 1, 0, the second line will select here, the second line will select here the value, here the input is equal to C bar, here the input is equal to C bar. Actually we have the given value is equal to C, C is equal to 0. If it is 0, you have to keep here 0, right? You have to keep here 0. Sorry, here C is equal to 0. Here C is equal to 0, but we need C bar. C is equal to 0, you put here 0, 0 bar, that is equal to 1. Here the input is equal to 1. This one goes to the output. Why? Because we have selected 1, 0 is equal to 1, 0 is equal to this second line. Okay, when you select 1, 0, here you will set the value is equal to C bar. Here C we have taken as 0. So the C bar is here, we have kept the C bar. C bar is equal to 1. That one value reflected to there. The one value is reflected to there. Okay, right. Next combination, these two combinations. Next, these two combinations. Coming to these two combinations, the AB values are 1, 1. The AB values are 1, 1 and C values are 0, 1. Here, when AB you are selecting as 1, 1, the fourth terminal will select. Here the fourth terminal will select. So coming to that, the C value, there is no necessity of taking the C value. Why? Because for these two combinations, AB value is there. When you select AB, this first terminal will be available. The first terminal will goes to as output. So with this, we have verified all the combinations. Now we will check one combination which is equal to 0. That means if you select this combination, if you select this combination, you have to get output as 0. You have to get output as 0. 0, 1, 0. So now I have selected here 0 and I have placed 1. When you select 0, 1, when you select 0, 1, this terminal will select. This terminal goes to selector. And here the value is equal to 0. This 0 directly goes to the output. That is F is equal to 0. Okay, up to now we have verified F is equal to 1 combinations. Now I have verified here 0 combination. If you select the input side this combination, the output automatically it gives the 0. So here I have selected 0, 1. Here I have fixed the value is equal to 0. This 0 is reflected there. So this is the given Boolean function implementation by using multiplexer. So this is not enough. With one problem we cannot get the complete data. So you have to practice more number of problems. So for this problem, this is the solution. Okay, right. Now coming to see one more example. So implement the function of full adder using multiplexer. Implementation of full adder using multiplexers. Okay. So here, so we have full adder truth table. Here we first have to draw the full adder truth table. So for the full adder truth table, x, y, z. No, we have three inputs x, y, z. 3 inputs are available from 0, 0, 0, 0 to 1, 1, 1 combination. And this is the sum values and these are the carry values. And this is the finalized expressions in terms of min terms, right? So here we have sum is equal to sigma small m of 1, 2, 4, 7, carry is equal to sigma small m of 3, 5, 6, 7. Here we have two Boolean functions. That means here we have two different problems. So if two equations are there, two different functions you have to implement two separate functions as with the help of multiplexer. So first take s is equal to sigma small m of 1, 2, 4, 7. So see here I have taken s is equal to sigma of 1, 2, 4, 7. So 1, 2, 4, 7. You here first what we have to do, highlight these values. First draw this table and represent all the min terms. So then highlight what are the values here they given. So here 1, 2, 4, 7 given 1. So 1 given, 2 given, 4 given, 7 given. So these are the values given here. Now here the final values. It is covered only one, that is the value is equal to C. That is the final value is equal to C. C, right? And it is covered by C bar. This is also covered by C bar and it is covered by C. Now in the place of I naught, you have to write down here C. And in the place of I1 you have to write down C bar. In the place of I2 you have to write down C bar. In the place of I3 you have to write down C. So now the inputs are here C, C bar, C bar, C. Okay. Now if you select 0, 0, if you select 0, 0, that is based on your combination. If you select from 0, 0, 0 to 1, 1, 1. 3 inputs from 0 to 7. If any combination if you select, you have to substitute the values. For example, take the combination of 0, 1, 1. Take the combination of 0, 1, 1. So the first two values are A, B. Write down here 0, 1. And the next value, this is C. C is equal to here 1. Now, when you select the 0, 1, when you select the 0, 1, this line will goes to select. This line goes to select. Here we have C bar value. If C is equal to 1, C bar is equal to 0. C bar is equal to 0. Right? So C bar is equal to 0. Okay, C bar is equal to 0, right? C bar value is equal to 0, then output is equal to 0. Then output is equal to 0, right? So coming to that normal truth table, 0, 1, 1. When you add 0, 1 plus 1, that is equal to answer is 1, 0. Where 0 is the sum and 1 is the carry. Here we are implementing the sum functionality. So here we have taken the combination of 0, 1, 1. That is equal to 3. That is not available in the given sum function. So that the output is equal to 0. If it is there in the given function, the output is equal to 1. Here we have taken the combination of 3. 3 is not available. We got the output y is equal to 0. Right? So now the Hence theorem is proved. So this is the example for sum expression. Next, coming to that, the carry expression. For the carry expression, so see here 3, 5, 6, 7 is given. Right? Now represent 3, 5, 6, 7. 3, 5, 6, 7. So here AB is covered 2 times. So for that reason, you have to represent this is 1. It is not covered, you have to represent 0. Now A bar B, it is covered only once, that is C. And this is also C. Now you have to write down these values. Now you have to write down these values. So here you have to write 0, here you have to write C, here you have to write C, here you have to write 1, and here you have to write A comma B values. Okay, here these values we have represented AB, and these values are 0, C, C, 1. These are the finalized diagram for full adder carry. This is the finalized diagram for full adder carry. Okay, so this is the explanation for the implementation of Boolean functions by using multiplexers. In this class, we have implemented a generalized function in the first 25 minutes, and the last 5-10 minutes we have implemented the full adder by using multiplexers. Okay, right. Thank you.